Hi everyone, this is Rasik Rashid Malik and today it is week 11 problem solving and discussion session for the course Fundamentals of Semiconductor Devices. Let's get started. I'll start sharing my screen. So I hope my screen is visible. So today we'll be talking about the heterojunctions. So far we have been solving problems related to the p-n junctions where the both p and the n side were made up of only one type of semiconductor material, and then it was doped with the p type on one side and n type on the other side. So today we'll be discussing about heterojunctions. So the first question here is, we have n germanium and p gallium arsenide heterojunction. So before starting this question, before solving this question, I'll give an overview of the heterojunctions. Let me share a new slide over here. So first is the homojunction that I was talking about. In homojunction, what happens, we have the same type of material. So we have same type of semiconductor material on either side of junction. Say we have a p-n junction, and on both sides, say this is silicon and this is silicon. So this type of junction is called a homojunction. But what about the heterojunction? In the heterojunction, so we have two different semiconductor materials. Are used to form a junction. Say you have material A and then you have material B, and you form the junction, and this can be of any type. This can be NRP, this can be NRP. Okay, so this is called a heterojunction. So on the heterojunction, since the two materials can have different energy band gaps, so there will be energy discontinuity at the junction interface. So I will write this point over here because this is very important. So in case of heterojunctions, the two materials will have different energy band gaps. So that means if the material A and material B have different energy band gaps, so there will be energy band discontinuity at the junction interface. So there will be energy band discontinuity at the junction interface. Okay, but since these two materials, say for example we have material A which has low band gap, and then we have say wider band gap material B. So when we make a junction out of this contact, so there can be the discontinuity in the conduction band, or discontinuity in the valence band energy, or both. So we will look into this aspect like shortly when we actually make a junction, heterojunction, and how depending upon the nature of A and B, and how the discontinuity will be there in the valence band energy or the conduction band energy. Okay, so before, let me start a new slide. So we now understood that when we have a heterojunction, we have two materials with two different materials, and those two materials can have different energy band gaps. But if we have to form a useful heterojunction, we'll talk about the lattice constants. So the lattice constants when we form a heterojunction of the two materials, so it will be useful only if we have the two materials, the lattice constant is almost matched. So the lattice constant should be, so the lattice constant should be well matched. For a useful heterojunction. Okay. This lattice match is important because any lattice mismatch can introduce dislocations resulting in interface states. Because if there would be lattice mismatch, so what will happen due to lattice mismatch? If we have the two materials, say we have a material A with say the atomic position is like this, and then we say grow or make a junction after material which has lower lattice constant. So what will happen? There will be strain developed in this type of a junction, so that we have to consider. So there will be strain developed in the top, in the material B, material A. So this we have to consider. So if there will be lattice mismatch between the two materials when they form a heterojunction, so that can introduce dislocations at the interface. Okay, for example, if we have germanium and gallium arsenide, germanium and gallium arsenide, so these type of materials have lattice constant matched almost around say 0.13%. Okay, Or similarly we have germanium or the gallium arsenide, aluminum gallium arsenide, because these type of heterojunctions are widely studied. Gallium arsenide, aluminum gallium arsenide. Okay, so for this as well, it does not vary far more than 114%, 0.14%. So this we have to consider about the latest constants when we have to. We cannot arbitrarily choose two materials and form a heterojunction, because there will be then lattice mismatch and it will create dislocations and then it will be more problematic. Okay, so the next is about the energy band diagrams. We will look into the energy band diagram, how the heterojunction energy band diagrams will look like. Okay, so now about the energy band diagrams. So since I was talking about that we will have in heterojunction, we will have a narrow band gap material and a wider band gap material. So we have the case when we have a heterojunction, we have narrower band gap material and we have wider band gap material. Okay, so the alignment of this band energies is important, because that will ultimately determine the characteristics of the junction. For example, we can have the possible cases of the band alignments of the wider and the narrower band gap material. Say this is material A. Let me insert a new slide. Say the option A is that we will have say this is my narrower band gap material and this is my wider band gap material. Okay, say this is EC1, EV1, and this is my EC2, this is my EV2. Okay, so this is the one type of where the forbidden gap of the wider material completely overlaps the band gap of the narrower material. So here in this case, the band gap of wider material it completely overlaps the band gap of narrower material. Okay, so this we have to consider. If this is the situation, this case is then called the straddling case, and most of the heterojunctions are this type. So this is case A, which we call as straddling case. So there are other two cases which I will draw. So if the band gaps are aligned like this, we have a narrower band gap material, and then we have wider band gap material. So here the band gaps are partially overlapped. Okay, so this type we have the EC1, EV1, we have EC2, EV2. So here there is partial overlap between the band gaps. So this type of junction is called as staggered heterojunction. And then there is third case where the band gaps are completely like they do not overlap. Okay, so that is called say, let me draw it first, then I will talk about this one. Say this is my narrower band gap material, and then I have a wider band gap material. EC2, EV2, EV1 and EC1. So here the band gaps are completely misaligned. So this type of heterojunction will be is called as the broken gap. Broken gap case. Broken gap case heterojunction. Okay, and but most of the heterojunctions are of type A, straddling case. So we'll be talking about this heterojunction here, and so this is the depending upon how the bands are aligned, we have three types of heterojunctions. Now depending upon the doping nature of the two cases, the narrower and the wider band gap, we have the four types of heterojunctions. Okay, so now depending on the doping, we have four types. So there can be cases where we can have, say this is my narrower band gap material and this is my say wider band gap material. So if one is of n type and another is of p type, okay, say this is of n type and this is of p type, so are the reverse, say the n type is the narrow band gap material and the wider band gap material is p type that I have shown here, and it can be reversed as well, like p type the narrower band gap material and the n type the wider band gap material. So this type of heterojunction is called as anisotype heterojunction. So this is called as, when we have, say here it is n isotype, we have the case that we have drawn is n on the narrowed side and p on the wider band gap side. So here we have used a notation, small cap letters for the narrow band gap material and the capital letters for the wider band gap material, or it can be reverse as well. It can be P type, the narrower band gap material, or I will write this way, starting from the N and P. We can have the wider band gap material as the N type, and we can have the narrower band gap material as P type. So here the capital letter indicators, we have a larger band gap material. So I will write it here, capital letter for wider band gap material. Okay, and then there can be the other case where on the both sides we have the same type of doping. Say, so this type of case is called as anisotype. Okay, then we can have another case where we have the same type of doping on either side of the junction. We can have, say, both sides the n type doping, or we can have both sides the p type doping. So this type of heterojunction is called as isotype heterojunction. Okay, and in this isotype heterojunction as well, we can have two types. We can have the narrower, we can have n and capital N, or we can have p and capital P. Okay, so these are called as the isotype heterojunctions. Now we will make the, since this is the isolated band diagram, we will take one of the cases. Say we will take one of the cases where say an isotype case, so where one side of the junction will be the of n type and the another side of the junction will be p type. Say we will consider the case, the one that I have drawn here, and we will try to write the diagram. So this way we can have the four types of heterojunctions, two in the anisotype and the two in the isotype. Okay, so now let's try to draw the energy band diagram for the case where we have n type and p type materials. We have to draw the vacuum level for reference, and we have to understand that, for example, let's business will be taking this type of a case, say the wider band gap and the narrower band gap case. So let me draw the first to the isolated band diagram. So first I will draw the isolated band diagram here. We have we have a narrower bandgap material, and then we have a wider bandgap material. So I'll keep it isolated for now. And I will draw the notation of various terms here. So when we have the isolated, so we'll have a common vacuum level. Let me draw vacuum level with some different color. So say this is the vacuum level, and then we have in the narrower bandgap material, say we will consider the case where this is of n type and the wider bandgap material is of p type. Say I will use now this red color for the Fermi level. This is n type and this is p type. So I will write it as E Fermi of the narrower band gap, which is of n type, and this is E Fermi capital P, wider band gap material, which is of p type. Okay, so and this is a special case of germanium gallium arsenide. Okay, this type of heterojunction where germanium is the narrower bandgap material and the gallium arsenide is the wider bandgap material. So the different terms here, this is similarly we have EC on the n side, we have EV on the n side, similarly we have EC on the capital P side and EV on the capital P side. Okay, and the energy band gap is, say this is the energy band gap here, which is EG on the n side, and then we have EG on the capital P side. Okay, and this difference over here, this is the discontinuity in the conduction band energy, and this is the discontinuity in the valence band energy. I will use different color because this is important. So the problems that we are going to solve, they have this common in case of heterojunctions. There will be asked about to calculate the different terms, which will be ultimately dependent on how the discontinuity at the heterojunction is. Okay, so I will write it as discontinuity in the conduction band, and this is discontinuity in the valence band energy. And here you have to understand that the electron affinity on the n side will be higher because this is the narrow band gap material, and in this straddling type of case, so the difference from the conduction band energy to the vacuum level will be its electron affinity. So I will write as E chi n, and this will be for the wider band gap material, E chi p. Okay, so this is the band diagram before contact. Okay, so the only thing is that we have to consider, you have to see here that the electron affinity of the narrower bandgap material will be less that of wider bandgap material, and delta EC is the discontinuity in the conduction band energy, and the delta EV is the discontinuity in the wider bandgap energy. Okay, so and if in case of ideal heterojunctions, but here we have in this diagram shown delta AC and delta EV. Let us try to calculate what will be delta AC and what will be delta EV. Okay, let me use the color of black color here. So the discontinuity in the conduction band energy. Okay, so if you see here from the diagram, the discontinuity in the conduction band energy can be simply calculated from the difference of the electron affinity, and in this case the electron affinity of the narrower bandgap material will be larger as compared to the wider bandgap material. So it is simply E chi n, the narrower bandgap material, E chi capital P, the wider bandgap material. So simply E chi n minus chi capital P. So this is the discontinuity in the conduction band energy. But what about the valence band energy? This can also be simply calculated from the figure. So we can write on the, we have to calculate this delta EV, so it is the difference up to the valence band energy. So how we can calculate it? I can write it as it is simply E chi n or this way, or we can calculate it from here. We can write the energy band gap difference. If I write the Eg of capital P, the wider band gap material, and if I subtract the energy gap of the narrower band gap material, so which is my delta Eg. Okay, so the difference in the band gap, and it is simply the discontinuity in the conduction band and the discontinuity in the valence band. So that means if we know the discontinuity in the conduction band from the electron affinity, we can calculate the difference in valence band energy. Delta EV will be simply delta Eg minus delta EC. Okay, so this is an important result, how to calculate the discontinuity in the conduction band and the discontinuity in the valence band. Okay, and another figure of interest is that of the Fermi level. Up to Fermi level we can call it as the Fermi potential or the Fermi energy, so which is called as the work function. So I can write it as, it is E phi, the semiconductor on n side, and this is E phi s, the work function on the capital P side. Okay, so this is a case before contact. Now we will draw the case of thermal equilibrium where these Fermi energies will be now aligned. Okay, so but if we have to match the two Fermi levels, what will happen at the interface? The electrons from the n gap, from the n region, the narrower band gap region, will move towards the P side, and the holes from the P side will move towards the n side. Okay, so this is the rule of thumb, and as in case of homojunction, this flow of charge will create a kind of depletion region or the space charge region in the vicinity of the junction. So, and the space charge width we will calculate later on the n side and the p side. So, let me draw the band diagram in thermal equilibrium now. So, this was the case of before contact. Now, we will draw the case after contact. After contact in thermal equilibrium. So, we have to draw now the common position of the Fermi level. So, let us say this is the junction line. So, this is the junction line, and so this is the junction line, and we have so this is the junction line, and I was saying that like far from the junction, this is the wider band gap material. Far from the junction, this will be a this is a p type, and as soon as we reach towards the junction, the holes will move across the junction, and so there will be kind of depletion near the depletion of holes near the junction. So the band diagram will look like this. Similarly, similar band will be there in the conduction band energy. Okay. So this is the wider band gap side, and in the narrower band gap side, so far from the junction, this will be of n type. But as soon as we oh, I have to draw it this way. So far from the junction, this will be of n type, but as soon as we reach the junction, there will be the depletion of electrons because they will move across the junction in order to establish the thermal equilibrium. So, and we have this the staggered case. So the valence band edge will look like this. Okay, so this is on the n side or the narrower band gap side, and so let me draw the notation again. This is EC on the p side, this is EV on the p side, this is EV on the n side, and this is EC on the n side, and this is EF capital P, and it is same as EF capital N, and here this is delta EC, the discontinuity in the conduction band, and this is delta EV. The discontinuity in the valence band. Okay, and we have the depletion width extended up to this region on the P side, so let me call it as XP, and we have the depletion width extended on the N side up to this point, say this is my XN. And corresponding to this depletion region, we have the potential developed. So let me, this is the potential developed corresponding to the depletion on the P side. Which I will write it as the barrier potential developed on the capital P side, and this is the barrier potential developed on the N side. Okay, so I will write it as EVBIN. Okay, and the rest is same. We have this energy band gap EG on capital P side, and we have EG on the narrower band gap side, and this is the position of x equal to 0 where the junction is formed. So and the bending in the conduction band in the valence band, we will have the similar bending in the vacuum level. So let me erase it here so that I can draw the vacuum level, and I will write this is the case of thermal equilibrium. After contact. Okay, so what I was saying, that I'll draw the vacuum level. So the vacuum level will be simply, there will be the similar type of bending as we have in the conduction band or in the valence band, and it will be continuous. So say this is the bending on the N side, this is the bending on the N side, and that was on the P side. So I'll try to write parallel to this conduction band and then parallel to the valence band. Okay, so this is my vacuum level, and the bending in the vacuum level, it is the sum of two bendings at the interface. So this is equivalent to this bending corresponding to E, the barrier potential developed on the P side, and this is corresponding to the barrier potential developed on the N side, and the total, the sum of the two barrier potentials will be the overall barrier potential that we might be required to calculate in the questions. Okay, so this is the ideal band diagram now, and similarly we can draw the band diagram for the other cases as well, So this was for the case of N and P. We can draw it for other cases as well, say N, capital N, or capital N small p, and other cases are the P sub capital P. So I will try to draw it quickly here. So let me insert a new slide over here. We'll consider the special case now of the isotype heterojunction. Say we'll consider the case of, which is widely used in case of gallium arsenide, aluminum gallium arsenide heterojunctions, or the gallium nitride, aluminum gallium nitride heterojunctions. So this is N and N. When we have the same type of doping on the two sides, and we will consider the case of, this will be the case of gallium arsenide and aluminum gallium arsenide, where this gallium arsenide can be of it is more lightly doped. It is lightly doped, or we can call it as even intrinsic it can be. And the aluminum gallium arsenide, it is of moderately to heavily doped. So let's draw the band diagram for this type of a heterojunction. Then we will discuss about the special features of this type of heterojunction, about the two-dimensional electron gas, the triangular potential well at the interface. So let me draw the band diagram first in thermal equilibrium. So in thermal equilibrium, what will happen? We will have the common Fermi energy, and then say this is the junction interface, and then as I said that about the wider bandgap material, it is more heavily doped, and then when the junction is formed, so it will be at the interface, what will happen? There will be depletion of carriers, so it will look more like this on the wider bandgap side, and there will be similar type of bending in the conduction band. And so the opposite case on the narrower bandgap material, so we will have the accumulation of the carriers. Or let me write this way. Since there is accumulation of the carrier, so the conduction band will be more like this. I have to correct these. So this is the narrower bandgap side, and this is the wider bandgap side. And we have delta EC, delta EV again here. So this is delta EC, and here it is delta EV. Okay, so and this is my bending on the VBI on the capital N side, the wider band gap side, and this is corresponding bending in the lower band gap side. And the rest is the same. So what you have seen here when forming this heterojunction, so we have the electrons from wider band gap material that is here aluminum gallium arsenide. They flow into gallium arsenide, right, and there they form the accumulation layer. Adjacent to the of electrons. Adjacent to the interface, right? And the accumulation of these carriers near the interface, so they result in the formation of the quantum well here. So this is the quantum well formation near the interface, and electron is contained in the, so electrons are here confined in the potential well. And they will form a kind of two-dimensional electron gas where the movement in the z direction will be confined, and so that is why it is called as the two-dimensional electron gas. So I will discuss it in the new slide. For this two-dimensional electron gas, its movement is confined in the plane which will be perpendicular to the interface, or the parallel to the interface. Okay, so this happens at the interface for these type of junctions. Okay, and if I draw the potential well, the potential diagram at this the interface, we can approximate it by the triangular potential well. So say, let me insert a new slide over here. So I was talking about we have a wider band gap material of aluminum gallium arsenide, and at the interface the band diagram will look like this. I should first draw the Fermi level. So this is my wider band gap material, and the narrower band gap material will be where there is the accumulation of electrons at the interface. So this will be the situation at the interface. We have a wider band gap material, aluminum gallium arsenide, and this is a narrower band gap material, gallium arsenide. Okay, so this at the interface we have this quantum well formation, and the potential can be approximated by a triangular potential well. Say this is my z direction along which this band diagram is drawn, so we can approximate it by a triangular potential. And in this triangular potential we will have the quantized energy level. Say this is my Fermi level, and we have E0, say we have the electrons contained in this level, E0 level. This is E1, E0. So we can approximate this potential at the interface by a triangular potential well. And the distribution of electrons in this potential well will be, we will have the electron density in this triangular potential well. A little away from the interface we will have the peak intensity of this electron density. Okay, somewhere little away from the interface, due to this quantization we will have the peak electron density. So since this gallium arsenide is lightly doped or intrinsic, this two-dimensional electron gas, so I will write it here. We know that gallium arsenide is lightly doped. So that means this 2D Eg that we have, this Nz, okay, is in a region of low impurity doping. So okay, so if it is in a region of low impurity doping, that means the impurity scattering effect is that we will, if we would have been the impurity doping or the impurity doping or the impurity scattering, I will write directly as impurity scattering effects will be minimized. So they will be minimized. So now the electron mobility will be much larger than if the electrons would have been in the same region with the ionized donor. So for the gallium arsenide it has a very high value in case of the mobility. So if I do not remember the values, but it is very high in case of the 2DG of the aluminum gallium arsenide. And this is very much interesting because this forms a very special type of transistors. This 2DEG can be used to make the special type of devices called the high electron mobility transistors, because since the 2DEG that is formed at the interface, it will have high mobility because it is in a region of lightly doped, since it is in a region of lightly doped region, so or which is the undoped region here that I have shown here in this case. If it is, I hope it is visible. So we have the undoped region, and then we have the carrier doped region. So this in this undoped region we have the 2D EG formed. Okay, since in the traditional design we will have the dopants and the carriers together, and then that will increase the impurity scattering and then decrease the degrade the mobility, and then in the transistors it will degrade the on resistance. But if we have to increase the mobility, we have to separate dopants from the mobile charge carriers. That is what gives us the advantage of this heterojunction, where we have the doped layer, the carrier doped layer, which is wider band gap material, and then we have the channel layer undoped material, which was in our case the gallium arsenide. So that result in the electron density with very high mobility, because that will have reduced scattering. Okay, and this the condition is that there should be the band gap difference between the two layers. There should be wider band gap and the narrower band gap material. Okay, so let me go back to my slides. So this is the advantage of these heterojunctions. So we have the moment confined confined in a plane which is parallel to the interface, and we will have the limited impurity scattering, and we can further improve it. Okay, so this scattering we will still have at the interface, we will have column interaction of the ionized impurities in the aluminum gallium arsenide. So it is not the electrons which are here, and due to the doping of the aluminum gallium arsenide side, we can still have some column attraction of the ionized impurities. So I will write it here. We will have still the Coulombic attraction of ionized impurities in the aluminum gallium arsenide. Right, and so which can be further minimized if we have to avoid the effect of the ionized impurities on the mobility of the 2D EG. We can use another type of heterojunction which is called as graded aluminum gallium arsenide heterojunction. Gallium arsenide heterojunction. So I will just draw the band diagram here for that type of a heterojunction, and I will move this to other side, and Z, and then Z. This is the distribution of the electron density in the Z direction. So I was saying that we can use the graded aluminum gallium arsenide heterojunction, so which will look like this. This is my intrinsic Fermi level, and then we have the gallium arsenide side. I will just draw the conduction band diagram, EC, and then at the heterojunction we will have the another insertion layer here, which will have the graded doping. So it will look like this. As compared to what would have been if there would have been just gallium arsenide. So this would have been, the band diagram would have been looking like this, and now we have region up to this which is undoped, and this is doped. So this can further limit the column scattering due to aluminum gallium arsenide, and this is EC, and this is EF. Okay. So just we have to sandwich and up to this is aluminum gallium arsenide, this is gallium arsenide, and this region is undoped. So we have sandwiched intrinsic aluminum gallium arsenide are graded, because that will slowly change from gallium arsenide to aluminum gallium arsenide. Aluminum gallium arsenide between N type aluminum gallium arsenide and intrinsic or very lightly doped gallium arsenide, right? So this is very much interesting, and it will increase the electron mobility further. Okay, now we'll talk about the electrostatics and say the equilibrium electrostatics. I will insert a new slide here now. And we will do it for the heterojunction that we have already considered in the previous case, the one drawn here, N and P type of heterojunction. So ideally I'll just move this slide, or I'll copy this slide over here. So we will calculate the total barrier potential, since this VBI will be the sum of VBIN and VBIP, and this VBI can be simply found the difference between the Fermi potentials, right? So because if this EFN is similar, so if we simply calculate the Fermi on the wider band gap side, the work function on the narrower band gap side, so that will give us the barrier potential. Okay, so from that we can actually calculate what will be the VBI. Okay, so let's start by doing that. So I will write this VBI is simply the work function wider band gap side minus work function on the narrower band gap side, and this is easily to visualize it from here. We have a wider band gap side, this is my phi SP and this is my E phi SN. So from the difference between the two we can actually this is the difference EVBI, right? So now going back to figure again, what is the value of this phi SP? So now we have to look into the figure again and calculate phi SP. So phi SP is simply, it is the E chi P, like up to this point, the conduction band energy. right, on the p side, and then we will sum it to the energy band gap, and then we will calculate this difference, which will be doping dependent, right? So I will write this this pi sp, I will write it as, in terms of energy, I will write evbi, and this will be e phi spn. So that will be equivalent to now e chi p plus energy band gap. So by summing the electron affinity and the energy band gap, we reach it up to the valence band, but we had to reach up to the Fermi level only. So we have to subtract this EFP minus EVP. So we have to subtract this difference. Right. So this is the first term. Now the second term will be similarly for the n side. We have to do the E chi n and then energy gap on the n side, and then we have to subtract the difference. So this can be simply visualized here, E phi n, then we added the energy band gap, and then we have to subtract this EFN minus EVN. Okay, let's go back to derivation. So I can write it as simply, this is E and the difference of the electron affinities, and then sum of the energy, the difference in the energy band gaps. And then EFN minus EVN subtract EFP minus EVP, right? So which can be further expressed as, this is minus delta EC, because we already know the difference between the electron affinities is the, from the narrower band gap to the wider band gap material, is the difference in the conduction band discontinuity, is the conduction band discontinuity, so it is minus delta EC, and then we have delta EG, the difference in the band gap, and then we can write it as KT, this is doping dependent, the difference between the Fermi and the valence band energy. So this I can write as KT ln of effective density of states of the valence band on the n side divided by the whole concentration. Okay, similar minus KT ln of NVP divided by P and P0. Okay, so the equation will be now summarized as EVBI to be equal to delta EV, because delta EV is delta EG minus delta EC, plus KT ln of, we can write these two logarithms as a one logarithm, and then this will be PP0 divided by PN0 and NVN divided by NVP. So this is the final expression where PP0 and PN0 are the whole concentration is in the P and N, materials, and NV represent the effective density of states in the N and P materials. And we can write it also in terms of the conduction band shift, as this is in terms of the valence band shift, right? So, and in terms of the conduction band shift, the expression will be simply EVBI to be equivalent to minus delta EC, and here it will be with respect to the conduction band states. Okay. So we can now start solving the questions. So the question here is about calculating the delta AC, calculating the delta EV, and we have the similar type of junction. We have N germanium and P gallium arsenide, the narrower germanium and the wider band gap as the gallium arsenide P type. Okay, so using this rule, the electron affinity rule, where the vacuum level was assumed to be continuous. So let's start calculating. So we know that from the previous calculations, we know that delta EC we have to calculate first. If I look into the band diagram again, the delta EC, or let me go to the previous slide again. So here we have calculated delta EC. Delta EC is simply the electron affinity difference between the narrower band gap and the wider band gap material, E chi n minus chi p. So I can directly write it here as delta EC is simply E chi n minus chi p, which will be equivalent to E. And what is the value of the electron affinity for the N type material and the P type material? Let me just write it here, because these are the materials. We can find it on Google as well. I have already noted these values. Chi N side, which is the chi germanium, so that is 4.13 E chi n actually, in terms of energy, electron volt, and then E chi p, which is for the gallium arsenide, which is 4.07. So we can write it here. These are the electron affinity values. So I should be writing it this way only. So since this is in the units of electron volt, so I can write this E chi n minus E chi p as 4.13 minus 4.07, so that is equivalent to 0.06 electron volt. So this is delta EC. This solves one part of this question, and the next part is about calculating the delta EV. So delta EV, if we look back into our derivation, delta EV was simply calculating the energy band gap difference, then that is equal to delta EC plus delta EV. So delta EV will be delta EG minus delta EC. So that will be delta EG minus delta EC. So that is equivalent to how much? 1.43 the energy band gap difference between the two materials, because for the germanium we can calculate these values online, or we can find the energy band gap for the germanium and for the gallium arsenide. So the delta Eg is 1.43 that I have already calculated, or I can write the values over here as well. Which is for the gallium arsenide, it is 1.42 around. So 1.42, and for germanium it is 0.7, right? So for gallium arsenide and germanium we can find then the difference. So that will be sorry about this value over here 1.43. So it is equivalent to 1.42 minus 0.7. So that will be 0.72. 0.72, and then you have minus 0.06. So this you can calculate as, which is 0.66 electron volt. So this is about delta EV, or actually the energy band gap for the gallium arsenide is 1.424. So this makes us the difference as 1.424 minus 0.7, so 0.724, and then we had to multiply by 0.06, so 0.664. So we can write it as it is equivalent to 0.7, right? And now if you have to determine the VBI, we have to determine the P on the N0, which we can found from and the P on the N0 in the germanium, which we can determine by so I can write as, because the VBI we have calculated here is delta EV, we have already calculated now KT ln of PP0, PN0, and then NVN and NVP. So we already know the values of NVN and NVP for the two materials, which I will just write, and P on P0 we already know, and then we have to calculate the minority of the P on N0. P on P0 we know. So P on N0 is Ni square divided by the doping. So that will be 2.4 into 10 power 13 square divided by Nd, that is 10 power 16. So if I use my calculator, so it is coming out to be 5.76 into 10 to the power 10 per centimeter cube. And now the other things are simple, because in the relation we have to calculate the PP0 that we already know. The doping is given as 10 to the power of 16 for the gallium arsenide and A. So let me insert a new slide now. So I can write it as EVBI, which we know is delta EV plus KT ln of P on P0 divided by P on N0 effective density of states in the valence band and these are the constants for the two materials. I'll just write their values over here. So this is 0.7, then 0.0259 for the KT, then ln of PP0, the doping is given 10 to the power 16, then PN0, the minority one that we have already calculated, is 5.76, 10 to the power 10, and then we have NV on N for the this is NV on N, and then we have NV on P. So we know these values are germanium and gallium arsenide, so simply 6 into 10 to the power 18 and 7 into 10 to the power 18 for the two materials. So if we calculate, then the VBI, this will be in the electron volts, so EVBI, so VBI will be simply, if I use my calculator, so that will be around 1 volt, the barrier potential. And you have to understand here that delta EC and delta EV is different, as we have calculated. For delta EC is very small and delta EV is very high, 0.7. So the what I am trying to say that the potential barrier seen by electrons and holes will be different. Okay, so this non-symmetry is not in case of homojunction. So what is the difference? The point to be noted here is that we have delta EC and delta EV different, non-symmetry. So due to this, we have the potential barriers seen by electrons and holes different. And this non-symmetry is not this. You have to note that this non-symmetry symmetry does not occur in case of homojunctions. Okay. So this solves this question, delta EC, delta EV and VBI. Now let's move to next question. So it is about the repeating the same example now, N germanium and P gallium arsenide. Only thing is that the germanium is now doped with 10 to the power 15 donors and the gallium arsenide doped with 10 to the power 15 acceptors, and temperature is same. So this is just the repetition of calculations here over here. So for the sake of this question, I will just solve it here. So we all know, you have to know that for this VBI, or we have to actually find the VBI. So we already know that delta EV is required. Delta EV we have already calculated in the previous example, and it was coming out to be 0.7 electron volt, right? Now, and the other thing, I will write the expression. We need Pn0 and Pp0 will be already given. So Pn0 will be simply Ni square and the doping of donors on that side. So this is 2.4 into 10 to the power 13. This was given in the previous question already, divided by 10 to the power 15. Okay, so that is now coming out to be 5.76 into 10 to the power 11 per centimeter cube, and EVBI can be then calculated as delta EV plus KT ln of Pp0, the doping on the P side, the minority doping on the N side, and these two are constants. So that is equivalent to 0.7 plus 0.0259 ln of 10 to the power 15, and this minority carrier we have already calculated, 10 to the power 11 into these values we know are constants for the two materials. So if we now calculate it, it is coming out to be the same 0.889 electron volt. Okay, let's solve now the next question. So here we have to sketch the band diagrams of abrupt this aluminum gallium arsenide and gallium arsenide heterojunction. So for the three cases where the doping is different, we have the case where aluminum gallium arsenide and intrinsic gallium arsenide is there, and then we have the N positive aluminum gallium arsenide and P type gallium arsenide, and then we have P positive aluminum gallium arsenide and N positive gallium arsenide. Okay, so let's, and then we have to repeat this problem assuming the ideal electron affinity rule. We have to calculate delta EC and delta EV. Okay, so we'll try to draw the band diagram first under thermal equilibrium. So for the three cases I will just I'll draw the band diagram for the first case. So this shows that we have the we have intrinsic gallium arsenide, and then we have, so for the intrinsic gallium arsenide, which is a wider narrower band gap material, say my intrinsic Fermi level very far from the junction, and then we have N positive aluminum gallium arsenide, which is a wider band gap material. Okay, so here what will happen at the interface, the electrons will move away from the junction, so there will be accumulation of carriers near the interface, and the similar type of bending will be in the valence band. So this is how the band diagram will look like. So this is the wider band gap material and the narrower band gap material, and this will be delta EC and this will be delta EB for this case, and this I will write it as gallium arsenide as intrinsic, and this is my N positive aluminum gallium arsenide. And there will be the next case, N positive aluminum gallium arsenide, and then we will have the P type gallium arsenide. Okay, so what will happen in this case, we have again the intrinsic Fermi level, and this is the interface. So here again we will have the wider band gap material, and originally it is P type now. Okay, so from the P type it will be less P type near the interface, so here it will be more bending. In case of a narrower band gap material. So only the delta EC and delta EV will change here, and so this is for the case of this is very highly doped P positive this is P gallium arsenide, and this is N positive aluminum gallium arsenide. And then there will be the third case where we will have the P positive aluminum gallium arsenide and the N positive so here there will be the reversal, because we have now the P type, the gallium arsenide, aluminum gallium arsenide. This is my Fermi level, and now what we have the P type, and near the interface it will be less P type. So this is my wider band gap material. Okay, then we have the N positive, so it will be more towards this, and then the depletion, very narrow depletion, the narrower band gap material. And the band diagrams will look like this. So this is my N positive gallium arsenide, and then we have the P positive aluminum gallium arsenide. Okay, so for the N positive and the P positive cases, we can draw this very close to the conduction band. Okay, so let me insert a new slide to solve the next part of this question. So the next part of this question is about calculating now the delta EC and the delta EB, and we have the values given. We have EG given for aluminum gallium arsenide for this special case, and delta EC as 2/3 of the delta EG we have to assume. So I'll write the values here. The delta EC is simply as a difference of the electron affinity on the N and the P side, and for gallium arsenide chi is 4.07, and for aluminum arsenide the same value is 3.5. and so this is the case of, let me write it this way, this is the case where, say, we have gallium arsenide on this side and we have aluminum arsenide on this side, and somewhere in between this is aluminum gallium arsenide. Say we have the band, this is about chi, and if the chi for the gallium arsenide is 4.07, say this value, and this is the 3.7 and this is 4.07, if I assume the linear approximation as the mole fraction of X, that is increasing from 0 to 1, X mole fraction of aluminum. So this I can write as aluminum X. So somewhere in between, for this special case of X equal to 0.3, we can if we calculate this electron affinity for that case, for aluminum 0.3, gallium 0.7 and arsenide, so chi is coming out to be 3.9. so this is the linear extrapolation. Okay, so we can then calculate the delta EC as, which is 4.07 for the gallium arsenide minus 3.9, so that is 0.17 electron volt. And how to calculate delta EV, that is delta EG minus delta EC, and EG we know. EG for the two cases, one is 1.85 and another is 1.42, so 1.85 minus 1.424, so that is equal to 1.85 minus 1.424, 0.424, 4 to 6 electron volt. Okay, so this solves this part of the question as well. So let's stop here. Okay, so I hope you understand this this lecture about this discussion session about the heterojunctions. Thanks for joining.